Hello, I am Itsaso Arrayago from the Polytechnic University of Catalonia, and I will present the work developed in collaboration with the University of Sydney on the statistical characterization of stainless steel structures with hollow sections for system-based reliability calibrations. This work is part of the New Genesis project, a Marie Curie Global Fellowship funded by the European Commission, which aims at developing system safety factors for the direct design of stainless steel structures. Current Eurocodes and other international standards conventionally adopt the member-based two-step design approach. In this method, a structural analysis is carried out to determine design forces, and resistances are then checked, treating structures as a set of independent members and connections. However, advances in design software have made it possible to accurately predict the behavior and failure of systems, and also to progress from member-based to system-based design methods using advanced finite element analysis. A few structural codes already incorporate direct design methods whose advantages are that the system strength can be directly evaluated from the analysis with no further member of connection checks, that lighter and more economical designs can be achieved, and also that we can actually see the failure mode from the analysis. The design process with these methods is very simple. We only need to run an advanced analysis using the design loads and to verify if the ultimate load factor meets the design check. The problem here is to get the appropriate system safety or resistance factor. If we look at standards, they only require that a comparable or higher level of reliability is achieved, but no values are prescribed for system factors. To overcome this, research has focused on the development of design recommendations for hot-rolled and cold-formed structures under different loading conditions in the last few years, but the method is still to be extended to other structural types or materials such as stainless steel. So as we all know, stainless steel alloys present a nonlinear stress-strain response with significant strain hardening and high overstrength ratios. This means that stainless steel structures have a potentially higher resistance reserve, but also that second-order effects can be amplified due to material nonlinearities, and therefore independent reliability calibrations are required for this material. So the objective of this study is to statistically characterize the main random variables affecting the strength of stainless steel structures, which will be the basic input information for reliability studies and the calibration of system factors. The methodology that we have adopted for this study is summarized in this slide. First, we assembled the different databases. For this, we collected measurements reported in the literature by international research groups, which were then compared with the corresponding nominal values using the information on the papers or in relevant standards, and the basic descriptive statistics were calculated. Then we selected the underlying distributions using histograms and previous experience on similar variables, and we fitted distributions to the data. And finally, the goodness of fit of the distributions was evaluated. The random variables that have been investigated in this paper for rectangular hollow section members refer to three main categories, which are the geometric properties initial geometric imperfections and material properties. Geometric properties included the outer section dimensions, thickness, corner radius, and member length, while initial imperfections at local and member levels were investigated. Regarding the material behavior, the key parameters for austenitic, ferritic, and duplex stainless steels were considered, including the Young's modulus, the yield stress, the ultimate strength, ultimate strain, and the parameters governing the nonlinear behavior. Obviously, there is no time to present and discuss all these variables, so we will go through a few in this presentation. For the random variables related to geometric properties, we collected a database with more than 1,000 specimens. And the analysis showed that all measured to nominal ratios could be represented by normal distributions with mean values very close to unity and very low coefficients of variation. These results are very similar to those reported in previous research for steel structures. For initial geometric imperfections, as we mentioned earlier, local and member imperfections were investigated. For both cases, imperfection amplitudes were found to follow log normal distributions, and the coefficients of variation were considerably higher. For local imperfections, the mean value of the gamma 2 factor was found to be close to the reference value, while the mean member imperfection was close to L over 3000, which is significantly lower than the L over 1000 reference value. The third fundamental source of uncertainty is the material. As we all know, the stress-strain curve of stainless steel alloys can be described by a two-stage Ramberg-Osgood material model, which depends on a number of material parameters. Design standards generally prescribe nominal values or predictive equations for these parameters, and in this study we have treated each parameter as a random variable. For the yield stress and the ultimate strength, we relied on previous studies that were based on a really extensive database, including results from producers, which proposed the overstrength ratios and coefficients of variation shown in these tables. So in this paper, we just focused on the remaining material parameters for cold-form hollow sections. For example, the Young modulus was found to follow a normal distribution for the three material types, and the mean values were found to be quite close to the nominal values given in the Eurocode for ferritic alloys, but significantly lower for austenitics, and the coefficients of variation were quite low in the three cases. On the other hand, the first strain hardening exponent n was found to follow a log normal distribution for the three stainless steel families analyzed. The mean values were also found to be slightly lower than the nominal values given in the Eurocode, and with quite high coefficients of variation. This is because the values in the Eurocode were average results calculated for different product types and rolling directions, while the data analyzed in this paper corresponded to cold-form material only. This is a process that tends to increase the roundness of the stress-strain curve and therefore reduces the value of n. So this was just an example of the analysis carried out in this study. The remaining parameters can be found in the paper. So this study focused on the statistical characterization of the main random variables affecting the strength of stainless steel structures in particular for cold-formed rectangular hollow section specimens. For this, extensive databases were collected from the literature on geometric properties, initial geometric imperfections, and material parameters, and probabilistic models have been proposed for the different random variables. This information will be basic input to calibrate system factors for stainless steel structures in the future. Before finishing, I would like to say that during the last months, this work has been further developed in different areas. On the one hand, the statistical characterization of random variables has been extended to different types of cross-section and also to additional random variables, including the enhanced resistance due to coil forming, residual stresses, and member imperfections. On the other hand, we have also carried out reliability analysis to calibrate system factors for stainless steel frames under gravity and gravity plus wind load combinations in different design frameworks, which are the US, Australian, and Eurocode frameworks. And we have also analyzed serviceability limit states. If you are interested, all this information can be found in the papers listed in this slide. Thank you very much for your attention.